Hello, this is part 2 of the introduction to the materials of structural masonry. In the first part, we looked at masonry units, mortar, grout, and both vertical and horizontal reinforcement. In this second part, we're going to look at the different elements of structural masonry, walls, lintels, and columns. TMS 402 provides a definition for a masonry wall. It's a vertical element with a horizontal length to thickness ratio greater than 3. So something has more length than thickness. So simply for an 8-inch wall, 24 inches long would be required to have a wall versus say something like 8 inches by 16 inches long would be then defined as a column. A load-bearing wall has loads greater than 200 pounds per foot in addition to the self-weight. When we look at designing masonry walls, again, designing with ASD or strength design, it's really not uncommon to have designs that have an H/T of 32 to 50. This is a quote from David Biggs. And in that quote, he also suggests that many engineers choose to avoid this method of design because they are not familiar with it. So it really gets back to some of the older provisions for designing masonry walls, which really current codes have replaced. So if we look at what the actual design for masonry walls would then result in, we have different wall thicknesses that can result in different heights based on that height to thickness ratio. So for instance, an 8-inch wall going from 20 to 33 feet tall would certainly be very common to do. A 12-inch wall going from 30 to 50, and a 16-inch wall in the range of 40 to 67 feet tall. Now, certainly if we wanted to look at those different wall options, one of the other things that I think we should consider was the actual efficiency of those different wall thicknesses. Certainly we can use a 12-inch wall for a shorter wall design. You can see here for a 10-foot wall, a 12-inch wall would be 10% more costly than an 8-inch design option. So certainly efficiency in the overall cost of the wall comes into play. And so certainly we want to use walls and wall thicknesses that make the most sense economically. And certainly if we need to, from time to time, use thinner walls, for instance, maybe a 30-foot wall, we could have different options of 8-inch, 10-inch, or 12-inch. Here you can see that masons maybe even prefer to use an 8-inch wall, even though it might be a little bit more costly, just because the units would be a little bit easier to work with. If you get into some of the taller walls, certainly that's when we want to switch over to a 12-inch masonry wall. Other things to consider as we look at different walls and wall heights, a 4-inch is available for both concrete and clay, but only the 4-inch clay masonry can be reinforced, and that's going to be pretty light reinforcement for that wall. 6, 8, and 10-inch are available for both concrete and clay, and both can be reinforced. And then really when you get to the thicker wall elements, 12 to 16 inches are really only available for concrete, and certainly those can be reinforced with fairly large cells. Within the different category of walls, we certainly have different wall types. We have shear walls, in which you could have load-bearing or non-load-bearing shear walls, but they're going to be resisting the in-plane shear force from something due to wind loads, seismic loads, could be earth pressures that cause a shear on a building, which would result in a need for designing those shear walls. In seismic design, we have different types of walls: ordinary reinforced shear walls, intermediate specially reinforced shear walls, and then certainly we still have ordinary and detailed plane unreinforced walls, although I would say that those are very uncommon for seismic design. The other category of masonry walls that we have that are very prominent in all areas of the country are going to be partition walls. It's going to be based on the code, based on both IBC and TMS 402. It's really going to be a wall that doesn't have really any other design other than holding itself up. We have to make sure that the wall can be stable. It's going to have very minimal amounts of design load that are going to be put on the wall. So it really, you can't have any in-plane forces, not going to really have any vertical forces, mainly going to be self-weight. It's really going to be a very simple wall design. And so really what that means is we really should be trying to make these very efficient elements within our buildings. See, because masonry walls are getting too complicated these days. There's way too much reinforcement. Studies showed significant costs related to partition walls because they're overly reinforced, overly connected to, and we really can start to realize some savings when we have partition walls that are not defined as shear walls. No reinforcement is required in partition walls. And then really looking at trying to connect these partition walls in as efficient and reasonable as possible. And certainly you want to make sure those connections are valid, though. We don't want to have any unintended loads. So as we're talking about partition walls, I'm going to bounce back to shear walls for just a moment. Looking at some of the different provisions that you have for shear walls, what I think is there's a couple of provisions that have had some carryover effect. There's certainly a design time, maybe shortly after IBC 2000 came out, when we had a lot of walls that would have been partition walls that participated in maybe some of the shear resistance in a building. We had some of those walls that are kind of in that gray area. So I think a couple of these provisions of reinforcement within the top of the walls, and then maybe reinforcement no more than 48 inches on center, those type of provisions that are now meant in today's code just for shear walls are maybe provisions that got some carryover into these partition walls, which by code today really has no load requirements. So some of these provisions, I'm hoping that we can maybe remove them from partition walls when they're not needed. Other ways to make partition walls a little bit more efficient is maybe utilizing IMI's free partition wall design software. It's a software that's available online. You can see the web address at the top. And that's really going to be a very good tool for looking at partition walls with very light loading. We can vary the different strength of masonry. As you can tell from the last talk, strength of masonry is going to be really important. So making sure that we have the right strength of masonry considered for design. And then you can see the actual partition wall requirements. You can see many of the different partition walls of all different thicknesses here. For much of the height ranges that we show within lower seismic design categories, those partition walls can still be unreinforced. And then when we start to reinforce them, we can start to use maybe bars at 8 feet on center. And so it really does allow for a very efficient design for your partition walls. So again, we really want to try to simplify these walls. We want to try to pull out some of the reinforcement that may be added. No need for horizontal reinforcement. We can really pull that out for lower seismic design categories. And quite possibly we can eliminate the top of wall bond beam. Certainly we can have connections at the top that can allow for the top of wall bond beam to be eliminated, which can be kind of a costly add. And then for the most part, quite often we can eliminate reinforcement or at least minimize it. We don't need to have reinforcement at 4 feet on center. Looking at the connections both at the top and the bottom, we can make sure that we have just the minimal connections that we need for partition walls. So again, we can make sure that we're cost effective. We have another paper from Force on partition walls, and we think it's a good paper in trying to define what the actual requirements are for partition walls so that we can make sure that it's as efficient as possible. So certainly contact IMI or Force to get this paper. The next masonry element that we want to look at is a masonry column. Column provisions within TMS and the old MSJC have certain requirements for the column sizes. So it's going to be a minimum side dimension of 8 inches. But then once we get into that column element, it has a reinforcement percentage of 0.25 to 4%. We have a minimum of 4 bars, and then we have lateral tie requirements of a 1/4 inch diameter, which would be a number 2, say, smoothed out tie that would be used for our column elements. We also have had lightly loaded columns that we can consider in lower seismic design categories. Really those elements that are going to be very little load, maybe a very small little canopy or something like that, where we can just have one number 4 bar as a minimum and no tie requirements. So that can be certainly helpful. But I think one of the things before we even get to a lightly loaded column, we need to make sure that we understand what a column is. Within the code, the element that's part of the wall that maybe beside an opening or something like that is really not meant to be designed as a column. So those elements that are integral with the lintels and the rest of the wall around it is not meant to be considered for the column provisions. It's just going to be for those isolated elements that are, say, supporting the end of the canopy. I think there can be a time, though, if we use some other material for the lintel, if we use a precast or steel element, then you possibly could get into a situation where that part of the wall that used to be connected to the lintel and connected to the wall above might start to be more and more isolated and maybe need to consider that as a column. So the different types of lintel choices that you make can have some bearing on how you design that element. It gets very costly if we have to start designing all of these different elements as columns because of the additional reinforcement and tie provisions. So here you can see a quick illustration of an element that, again, if we had a masonry lintel, could have been designed as part of the wall, but here you can see this ends up being a column element with the steel lintels completely cutting off that element from the rest of the wall. Since we're talking about lintels, you can see that for masonry, lintels are just going to be the area above an opening that's going to span the opening. You have several different options that people have used in terms of different materials. Masonry materials for a masonry lintel is hopefully pretty straightforward. It is going to be the best option because it's going to leave the masonry lintel to be integral with the wall. It's going to allow the jambs on each side to be designed as parts of the wall and not as a column. So masonry lintels, they're really going to make the best option for both structural and architectural considerations for that wall. Steel is also an option. It's something that's been used quite a bit. Generally, it's going to be used for trying to simplify the construction, but hopefully we can show in a couple slides how that's definitely not true. Well, we have a future presentation that focuses entirely on lintels. One of the main parts of that presentation is showing all the different complexities that a steel lintel creates and how it actually has less capacity. The wall has a less capacity with a steel lintel than a masonry lintel. We also have a precast lintel option, which is kind of a little bit of both. It's going to be an isolated element similar to steel, but there's going to be precast materials that can make it a little bit more like a masonry element. So why don't we just talk about that one just a little bit. The precast lintels that I'm looking at here is where the actual lintel is going to be really created to be similar to what would be a lintel block, but a very long lintel block. They're going to have some embedded tendons in them and really allow it to span the opening as you are building in construction of the masonry wall. It's still going to be an isolated element, but it really does allow for reinforcement that works pretty well with the wall. So it needs to be modular with the masonry. Special anchoring might be required depending on the size and length of it. It's a coordination issue. It's certainly different than you're going to be supplied from a different location than the overall blocks. And so then it could be somewhat of a scheduling issue. Steel lintels, as I said before, are certainly going to be common, but should they be? It really were created for eliminating shoring, right? If you can set a steel lintel, you don't have to put in the shoring, and you really can kind of keep building with the wall. And so I would suggest that the precast lintel that we just looked at is going to be a much better option than steel, and also not require shoring. So you definitely have options, and we'll talk about masonry lintels that don't require shoring as well. So it's definitely a scheduling critical item. You definitely has a much longer lead time than block. It needs corrosion protection, flashing, and treatment. I mean, certainly the rest of the wall is not going to need the same type of treatment that you're going to need for the steel lintel. Bearing plates are often required, just another coordination issue and an element that has to fit within the masonry element. And then thermal bridging. Thermal bridging, I think, is an issue that we're looking at architecturally in terms of seeing what the transfer of environmental elements from the outside to the inside. That cold on the outside really does cool down that steel lintel and transfers to the inside. It's also an issue, not just architecturally, but structurally. So as we think about that steel lintel carrying in that cold from the outside to the in, What you also have to think about is the actual steel element is going to be shrinking. It's going to be getting smaller because of that thermal loading that the rest of the masonry wall isn't going to see. So you really have a steel element that's going to be changing size, changing length, when the rest of the masonry wall that's behind insulation, that's a lot more mass, is definitely not going to have the same conditions. It's not going to be changing size. So that really does have some demands and create some bearing issues for those steel lintels. Does definitely leads to a lot of cracking in masonry walls because of those steel lintels and how they're connected to the masonry around them. That's really not moving. So thermal bridging is definitely an architectural issue, but that differential movement that it causes is very much a structural issue that we have to look at. Here you can also see within the image to the right, there's a little bit of a torsional issue that you have to consider. Does the actual steel lintel work for torsion? If it doesn't, you could have some warping of the steel lintel. If you solve the torsional provision for the lintel, you still have to solve how it connects back to masonry. It might be a very rigid connection that you'd have to use to resolve the torsional forces at the end of the steel lintel. So you need a flexible connection because of the thermal issue, but then you need a very rigid connection because of the torsional issue that you have for a steel lintel. So they get pretty complicated pretty fast, and I think they can be something that really were only introduced to eliminate shoring. So I think really what we want to look at is can we do this same thing with masonry? Something that's fast, economical, matches the rest of the wall, moves at the same rate of the wall. We're not going to have any of those thermal issues with a masonry lintel. And it really is prefabricating masonry lintels that can really allow us to solve all of the problems that we were trying to solve with steel, but we have to prefabricate them, and prefabrication is becoming much more commonplace for all different construction materials. So we can see that in masonry that has some huge advantages when we can prefabricate a masonry lintel. Really with masonry lintels, any length is possible. There's really no length restrictions. You can span 20, 30, 40, even up to 50 feet with a masonry lintel. And really the longer the lintel, sometimes people have said to me, well, Sam, maybe masonry lintels work for some of the shorter openings, but if you get into the longer openings, then we'd have to use something else. And I would actually argue that the longer the opening, the more it makes sense to have a masonry lintel that can work with the jambs in the wall around it to span the opening. It's going to be a lot less stress concentrations if I have a masonry lintel versus if I have some other material in there trying to span the opening that's going to have a lot more higher stress concentrations and more potential problems the longer the opening. Again, lintel elements within the code, it's pretty common to have bottom bars. Top bars are becoming more common with finite element designs. We can introduce stirrups into lintels if we have very limited depth, but it's going to be a lot easier to simply add more courses and add more depth to a masonry lintel to solve for that shear and not use stirrups. But stirrups are a potential option that you can consider. And then you have the code defining certain lengths based on the span plus the depth of the lintel. And again, you can always consider horizontal bending in addition to the vertical bending, and that's going to be a lot easier to do with the masonry element as well. Other things that we have for lintels that NCMA gives a nice tech guide to looking at arching action for masonry lintels, and really what that, if you can envision how that works, it's really going to be allowing the wall to work in addition to just the lintel. So the lintel is really only picking up some of the localized load to the lintel itself, and then the wall spans the opening. If we have a lot of arching that we can achieve with the wall. So really what that means is, the control joints, we talked about the control joints in the last talk a little bit. We want to make sure that that control joint is not too close. We want to be able to have that arching that's going to come down and have a vertical and horizontal component, that horizontal thrust load. If we have a control joint that's going to be close to the edge of the opening, then we're going to eliminate the ability for that thrust load to be transferred. And so then the arching action would go away and the lintel design goes up much higher. So we want to make sure control joints, again, stay away from the opening, and we can design our openings more effectively, again, with control joints away and masonry lintels. Again, finite element analysis really does help a lot with masonry design. maybe no more so than with the lintels. You can see what the actual forces are, bending moments and such relative to the different areas along the length of the lintel. And we can really evaluate then the stresses and forces just for those particular elements that are localized to the opening, which would be considered the lintel. So lintels are going to be a lot more integral, more robust element. And really, you can see here just by exposing the reinforcement, you have a very robust connection that you have with the reinforcement when you can have the reinforcement from the lintel and the jamb crossing one another, and it's going to be a much more efficient design. So next we're going to switch back to wall groups, more suggestions for control joints. We talked about when to use control joints, when not to use control joints, maybe some reinforcement, horizontal reinforcement considerations for using control joints. Really, when we look at these different elements, when I'm putting on a little bit of a different hat for masonry design, if I have a boxed wall group, if I have a stair or elevator shaft that I want to look at for design, really these elements are probably going to be small enough that I don't need to add control joints because of overall length of wall. I maybe have some openings, but just like for the lintels, I don't want to have control joints near openings. Here for these shaft walls, I have an additional reason not to put control joints in. If I put them in, I reduce the overall capacity of my wall group, my lateral in-plane shear capacity. Really, if I put in control joints, then all of a sudden I have just parts of those shafts that are able to resist the load. You can see by the blue arrows, you can see the long walls are going to be the only elements resisting the load in the direction of the wall. I don't have any additional flanges that I'm going to be able to utilize for resisting that load. And then conversely, if I follow the green arrows, you can see that those short walls then are also working by themselves trying to resist the load just in that direction with very small flanges. So the overall capacity of those stair and elevator shafts are going to be much higher when we eliminate control joints and look at boxed wall groups. You already probably have horizontal reinforcement near the openings and at the floor lines, and there's plenty of reasons for adding a little bit more horizontal reinforcement and eliminating those control joints and having a much stronger system design-wise. So again, for in summary, here we talked today a little bit more about the walls, lintels, and columns. We're going to have many different future presentations that are going to get much more specific into stuff like masonry lintels and stuff like masonry shear walls. We'll also look at movement joints in a much more specific way, so you can see how all of those things are coming together for our overall masonry design. Certainly, if you have any questions based on this video, you can send me an email at sam@forceconsulting.com. And again, some of the different key points from the last two videos, we really want to make sure that we understand masonry materials. We understand F'(M) being 2,500 or more, and how we achieve that, how we need to specify different types of materials. We want to think about control joints. When we want to have control joints, maybe when we can eliminate them, how control joints are located relative to openings, and then understanding some of the different wall options, unreinforced partition walls. We talked a little bit about lintels and a little bit about shear walls. Software is going to be something that's going to be very key for having a very good understanding, and we're going to have future presentations on finite element software and all software for masonry design as well. So really trying to look at engineers using the full capacity of masonry. Again, we created another little white paper for those considerations to make sure that we can be kind of back checking and making sure that we have a very efficient masonry design. So again, some of the future presentations you're going to see here on screen. And all of these presentations are brought to you from the International Masonry Institute in our Structural Masonry Design webinar series. So maybe make note of any of the specific topics and days that you want to attend any of these presentations. And again, my name is Sam Rubenzer. I work at Force Consulting with a lot of other engineers. We have many different types of buildings that we worked and did designs for over the years. So hopefully you can join us in future presentations for the structural masonry webinar series.